Hi, Mr. Yeager again. This is a pretty short topic for this particular recording. We are only going to be quickly looking at the idea of work being done by a variable force. Okay, this is where instead of you just constantly pushing at 100 newtons, what if you push at 100 newtons for 2 seconds and then 50 newtons for the next two and then negative 50? What happens with this particular problem? It sounds really complicated. In the end, it all comes down to graphing. Okay, we're going to have to do a graph. All right, so let's jump right into it. All right. We already know that work is force times distance. All right. So if I want to create a force times distance graph, all right, what would be the area under the line? All right. So before I jump into this, just to make sure we're clear, whenever you get a graph problem, whenever there is a graph given to you, all right, you should know these are problems where they're basically saying you're going to do one of two things, most likely. Most likely. Either the slope means something or the area means something. All right? If it's the slope, we are figuring out that the y-axis divided by the x-axis means something. For the area, that means the y-axis times the x-axis will equal something. Okay? Y times x will equal something. All right? So that's what we're doing here. If I have a force versus distance graph, force, distance. All right? What happens if I find the area? The area would be force times distance. Whoop! Area is going to be work. All right? The only thing you got to pay attention to, though, is it positive work or negative work? Is it above the x-axis or is it below the x-axis? That's all we're paying attention to. Okay? So, here's just a quick graph. You can see what we're doing here. Force, distance. All right? Area under that line would be force times distance. This particular graph is basically showing you one force. All right? So nothing too special there. We would normally just say, oh, I'm using this particular force for this long, this much distance. I'm good to go. Force times distance would be the work being done. Okay? So area under the line is equal to work, which equals a change in energy, which we're really going to hammer into in the next recording. Work causes a change in energy, any type of energy. All right? If you have to do a force distance graph and it is a triangle, guess what? We still find the area. It's just 1/2 force times distance. Okay? We just have to do the 1/2 force times distance. Work would equal 1/2 force times distance because it's a triangle. All right? And so I think we have a quick problem here. Oh, no. We go through this one. Yeah, this is a quick problem. Okay? Let's try to figure out the total work being done on this object. How do we do this? We would split up the graph like it's already done for us into a bunch of different parts to figure out the area of the whole system. So if I look at the first part here, 4 times 5, this is the area, just a little rectangle. This must be 20 joules. Now, is this positive or negative? It's above the x-axis, so positive. And I look in the next section. Okay? Might change this into a triangle and a rectangle instead of a trapezoid. If you know how to do trapezoids, do trapezoids. I just know people struggle with those. This would be 3 times 4, that would be 12 joules. This would be 2 times 3. So 2 times 3 is 6 times 1/2. That would be 3 joules. All positive still. And I go to the other side. 3 times 6, 18 times 1/2, 9 joules. So if I said what would be the total amount of work being done over the first 11 seconds, I'd add all of these areas above the line up. But I don't. I'm not done. The force switches direction. Now I'm pushing the opposite direction of the motion. Still moving forward, 11 to 15 meters. Okay? But now the force is backwards. So I can just calculate this whole triangle together. 4 times -5 is -20 times 1/2 is -10 joules is done during that time. So if I add all these up, 20 plus 3 plus 12 plus 9 minus 10, that gives me, fill in that 20 there, 23, 35, 44 minus 10, 34 joules is done on the object. It gains 34 joules of energy. All right. So, so this is basically leading us into our next section. All right. If I have just a basic problem, so this is kind of the go ahead into what are we going to do next? What's this covering next? I have a 1 kilogram ball pushed with a force of 20 newtons horizontally for 10 meters. How much work is done? I'm going to be very brief with this. The object's being pushed 20 newtons for 10 meters. As you can see, the answer is 200 joules. What does that mean, though? Okay, what does this lead to? All right, and so this is what's getting us into our next section on work energy. All right, this work is going to create a change in energy. What you need to figure out is this change in energy a change in kinetic energy or a change in gravitational potential energy. Well, if it's on a horizontal surface, I'm assuming what's the ball going to do? It's going to speed up, and it's probably the kinetic energy that is increasing with this work being done. So that's for another time. Thank you very much. I think we're done for today, and we'll go from there.